Hey people, this is a problem from RMO 2023. So I I think it's the first problem. Let n be the set of all positive integers and let s equal to abcd such that a square plus b square plus c square equal to d square. Find the largest positive integer m such that m divides abcd for all abcd belongs to s. So we will prove that the answer is 12. Answer, if any of you wants to know the answer is 12. And first, let's take a case. Notice that 2 square plus 2 square plus 1 square equal to 9 equal to 3 square. So, what is the product ABCD? ABCD equal to 2 into 2 into 1 into 3, which is equal to 12. So, our answer cannot be greater than 12 because we got a case where the number itself is 12. And if our answer would be greater than 12, how can that number divide 12? So, answer is less than answer. From this, we get that answer is less than equal to 12. Okay, more specifically, the divisors of 12 are the only possible answers. Now I will show that 12 itself can be obtained. So our equation is a square plus b square plus c square equal to d square. We will prove that. First we will make a claim. Claim is that 3 divides a, b, c, d. Okay, so this is the claim. Uh, for the proof, assume not. Assume not. Okay, then none of these numbers is a multiple of 3. A, B, C, D, none of them are multiples of 3. Okay, and from that we can get that. Notice that if 3 does not divide A, then A is congruent to either 1 or 2 mod 3. And in both these cases, A square is congruent to 1 mod 3. This is what we get when 3 does not divide A. And similarly, 3 does not divide B and C. From this we can conclude that A square plus B square plus C square congruent to 1 plus 1 plus 1 is congruent to 3 is congruent to 0 mod 3. And because a square plus b square plus c square is equal to d square, so we get that d square is congruent to 0 mod 3, which is a contradiction. This d square is congruent to 0 mod 3 basically gives that 3 divides d. Okay, and this is a contradiction. So we get that 3 divides abcd. So 3 divides abcd. This is our first thing we got. Next, we'll prove that 4 also divides abcd. Now the second claim, claim 2, is that 4 divides ABCD. Okay, to prove that proof, we'll again assume not, and we'll further take two subcases. Suppose we do subcase 1 is that 2 also doesn't divide ABCD. 2 also does not divide ABCD. This is the symbol for does not divide. In that case, A, B, C all are odd numbers, and note that if 2 does not divide A, we can get that A square is congruent to 1 mod 4. This can be got in exactly the same manner in the previous claim. This is not very hard to show. So A square is congruent to 1 mod 4. And if we sum of all three terms, we get that A square plus B square plus C square is congruent to 3 mod 4. Okay, but notice that we have assumed that 4 does not divide anything. And in particular, 2 also does not divide anything. So this congruent to 3 mod 4 is unobtainable in the case of mod 4. So d square is congruent to 3 mod 4 does not have any solution. How can we check this very quickly? So d can be either congruent to 0, 1, 2 or 3 mod 4. 4. And in that cases d square is congruent to either 0 or 1 mod 4. You can easily check this. Okay, so 3 mod 4 doesn't even exist as a solution to mod 4. This was our subcase 1. So this is not possible basically. D square is congruent to 3 mod 4 is not possible. So now we will do subcase 2. Subcase 2 is that 2 divides ABCD, sorry, 2 divides ABCD, but 4 does not divide ABCD. This is our second subcase. Notice that if 2 divides d, then 4 divides d square. Okay, so if 2 divides d, then 4 divides d square. Thus, d square is congruent to 0 mod 4, and this is congruent to a square plus b square plus c square. And notice that because 2 divides d, 2 cannot divide any of a, b, c, and in a manner similar to the previous case, we can get that this is equal to 1 plus 1 plus 1 is congruent to 3 mod 4. This is a contradiction, okay, because 3 is not congruent to 0 mod 4. And if 2 does not divide d, then 2 divides one of a, b, and c, exactly one of a, b, and c. It cannot divide two of them, otherwise 4 will divide a, b, c, d. So suppose, without loss of generality, basically means is that the other cases are symmetric. Without loss of generality, 2 divides a. Then what do we get? A square is congruent to 0 mod 4. If 2 divides a, then 4 divides a square, obviously. And we get that b square is congruent to 1 and c square is congruent to 1. So what do we get? A square plus b square plus c square is congruent to 2 mod 4. And this is also congruent to d square. And notice that I had showed that d square can be congruent to either 0 or 1 mod 4. So 2 mod 4 is a contradiction. So we are also done with subcase 2, and we had earlier showed subcase 1. So our claim is already proved that 4 divides ABCD. Okay. Now from our two claims, we will get that from our two claims, 3 divides ABCD and 4 also divides ABCD. So from these two, we can conclude that 12 divides ABCD. Okay. And this is the largest number we can get as I had shown earlier. So 12 is the answer to our problem. All right, thanks.